Okay, general relativity. Now we're going big time. No, this is actually where we really get into, oopsie, uh, more difficult to understand. Certainly, here's the equation for it. More difficult to calculate. I always see there's a t-shirt that has that on it. It says, what part of this don't you get, right? Um, looks like a small equation for how many years Einstein worked on it, but you might recognize a few things in here. Big G should look familiar. C should look familiar, and oh, pi, that should, eight's familiar. Little g is the field constants for sure. This is all, it's a formula of gravity is what it is, right? But it's gravity, which is non-inertial reference frame. It's very, very complicated. And so all I want to tell you about it is, yeah, what is it? A theory of gravity that's proven to be true, and it is in conflict with universal gravitation by Sir Isaac Newton. So it was very controversial when Einstein came out with it. However, like everything else, it's been proven to be true. But we use Newton's universal gravitation all the time, and physicists use it all the time, engineers use it all the time, because it's not as true as this, but it's a really, really good approximation. Okay? Yeah, so that's what it is. It's how he explained it. And this stupid little picture, though, it's supposed to show that, so for Sir Isaac Newton, everything, this is Sir Isaac Newton, Einstein, space was linear. It was absolute. It just a meter is a meter is a meter. Similar time. Time, a second is a second is a second. Well, Einstein showed that to not be true. He showed that space curves. Space does not follow a nice linear pattern such as this. And we hinted on that when we talked about special theory of relativity, with the idea that depending on how fast you're going, there's length contraction. And it's to do with the idea that if there's only one absolute, and that's the speed of light, then nothing else can be. So we just wanted to give you some ideas of things he thought about, things that have been observed since then relative to general relativity. Let's just take a look at this. So imagine, I guess what I'm saying here is, imagine that here's somebody on an elevator. These are supposed to be the same person elevator. This is like regular life. This is pretend you're in an area of zero gravity. Okay? Now watch. Okay, let's do this again. Now keep in mind, what are we looking at? We're looking at this guy's moving, this guy's staying still. They both toss a tennis ball. And from their perception, it looks the same. And it's the idea that, what we see as gravity, we think of, regular gravity, we think of, you throw a tennis ball up, eventually it's going to come back down again. Let's just think about this. This is about what you expect. You throw a tennis ball up, it's going to come back down again because of gravity, as Sir Isaac Newton explained it, and as we calculate several times, right? What Einstein said is, well, there could be zero gravity, it could just be us moving. And that's what we observe, is our motion relative to the ball, right? And it's this idea, and this gets really complicated, that, the Earth is pushing up on us, kind of like a normal, it is a normal force, but it's pushing up on us, and that's what we observe as gravity. It's actually moving into our feet, and that's why we feel pushed into the ground, and that's what gravity is. It's hard to understand. Here's another thing it tells us. Here's a little bit Alice in Bob.
Wondering about time travel. Says here, Einstein figured out that time slows down closer to massive bodies, like a black hole.
So we could use it as a time machine?
Let's try it. I'll lower you down, closer to the black hole.
I'll count to 10, then pull me up. Don't let go. 1, 2, 3. I don't feel time slowing. But look how gravity bends light, distorting the view. 8, 9, 10. Pull me up, Bob!
Alice, at last!
Oh, in 10 seconds you became a man.
10 seconds your time. 10 years, my time. Time moved more slowly for you relative to me.
My tree! It's also grown up! I've traveled into the future. Einstein discovered powerful ideas.
Okay. So that's another thing that he predicted. And I hinted at that when we talked about the idea of the clocks on the satellites. There's two effects of being up in space, like Bob there, right? His time was moving faster because he was away from a gravitational field. However, the fact that he was probably moving very fast would have offset that a bit. There's two sort of conflicting. We only calculate time dilation related to special theory, which is motion. We don't calculate it related to general theory. Not because you're not smart enough, because you actually are. It's not that hard, but it's only so much time. What does general relativity tell us? Oh, Einstein predicted the existence of black holes well before there was ever an observation of one, right? The first observed one was, I want to say 1972 or something like that. Einstein was long gone by then, but he predicted it because of the warping of space around bodies with mass, objects with mass. Yeah, he also predicted the Big Bang. He actually thought it was a mistake. So thinking of the Big Bang as not, an explosion and everything sort of grew out, but there's the space that's already there. It's the idea that the Big Bang, there was everything was all matter, everything that existed was in one tiny, tiny little infinitesimal spot. Not just matter, but space. There was no space outside of the Big Bang, which it hurts. Again, when I was at the Perimeter Institute, and they were talking about all the one lecture I sat in on was going through the Big Bang, right? And they can predict with so much precision, what happened like 10 to the negative 20 seconds, like 0.00000 seconds after the Big Bang. But if you ask anything about before the Big Bang, he always had the same line, which is, that's where the dragons live. So Einstein predicted all this stuff. General relativity predicts the expansion of the universe very nicely. However, there's no explanation, scientific explanation for before the Big Bang. Nothing of any credibility at all. There's guesses, there's thoughts, but zero science. Yeah. So this is kind of what it is.
Think of empty space, or actually empty space-time, as a rubber sheet, like a trampoline. A heavy object like the sun will actually bend the sheet, and the heavier it is, the more the sheet, space-time, is bent. Now, if you now roll a lighter object, say a planet, along the sheet in a straight line, the curvature of space-time will cause it to move in a circular path around the heavy object. The planet is actually following a straight line, but in curved space.
So what that says is, the reason why, think why gravity? And actually gravity, even with relativity, is still very not understood by physicists. Why is it that two objects with mass attract each other? They can explain it pretty well with electromagnetism, with everything, but not gravity. And Einstein, the theory of special relativity, which, by the way, the word theory, what does that mean? Right? It's a theory because there's math behind it, there's evidence for it, but it's not a fact. You know what I mean? Like, it's difficult to say something's a fact. It's still a theory, right? It's just that they can use it very often and predict things with it, right? It works very well. Anyway, so the idea is this idea of you've got a big sheet, you stick a mass in the middle, and then you shoot a marble, and the marble should orbit that mass, right? And eventually it'll fall in, but that's basically how Einstein predicted space is. It's just like that. The other thing, kind of using the same model, is that, and this is how he actually finally proved it, was that we from Earth we see a star, we think it's over here, but in fact that star is way behind back there. It's just that light bends, the light from that star gets near the sun and bends, and that's called gravitational lensing. So what we see, where we think that star is and where it actually is, are two different things. And that's kind of how they ended up proving that 1919. So He finished writing up his theory for general relativity in 1914 or 15, but there was no evidence for it. It was just his theory. And again, it was very highly disputed because it conflicted with Sir Isaac Newton. However, some astronomers, this is Eddington, in 1919, using an eclipse, he could he could see the motion of light from a star behind, and when they knew where that star should have been, it really completely validated general theory of relativity. And so that one experiment, then all of a sudden, this is when 1919, Albert Einstein became a celebrity. Then everybody loved him. So he came up with a theory. 4 years later, this guy proved it, and Einstein becomes the celebrity. Yep. So evidence, evidence that they've seen besides the light bending. Eddington, that was the first. The clocks, I told you about that already. When studied closely, the orbit of Mercury around the Sun, if they actually measure it very closely, it might be expected to follow this model according to Newton. But according to Einstein, it would follow a path like this around the Sun. And of course, with close observation, they found that yes, this is actually the path it does follow. This is an exaggerated picture, of course. It's not that obvious, but that's what it is. Okay, so that was another piece of evidence that supported Albert Einstein's theory of relativity. Okay, that's as far as we're going on relativity.